11.1. We're starting the chapter over statistics, descriptive statistics, so you can see is what we're focusing on in this particular lesson. Chapter 11 deals with all types of inferential statistics. So let's get going first with our bell ringer here. On number 1, it says find the rectangular coordinates for the point 3, pi over 4, given those polar coordinates. So 3, pi over 4 is polar, means we're going to be on this third circle, somewhere on this third circle, and specifically that somewhere is the pole pi over 4. So if I go to pi over 4, where these two meet, this would be my point A right there. And it says find out what those values are in rectangular form. Well, the formula we learned last class is to find your x, you will take the r and you'll multiply it by the cosine of theta, where for any polar coordinates, the points come in r, theta. So the x value would equal 3 times the cosine of pi over 4. And I'll pull up a unit circle in a second. The y value is going to equal r sine theta, and y then, when I plug in, I substitute my values, will be y sine of pi over 4. Okay, so now what I'm going to do first is I'll show you by algebra what the values are. Given this unit circle here, pi over 4, the cosine is square root of 2 over 2, the sine is square root of 2 over 2. Now let me shrink that a little bit, and I'll just move it up to the side up here. So these two values, like we said, we're looking at pi over 4. This is the cosine, and this is the sine. It's the order that it comes in. So what I would have here is x would equal 3 times, and I would substitute in here square root of 2 over 2, and y would equal 3 times square root of 2 over 2. Thus, when I simplify, nothing cancels out with one another. B would be my answer choice here. By way of the calculator, if you went down to calculator 28, plotting points, polar and rectangular, and opened up that graph or that calculator, specifically I'm dealing in the mode of radians, so I need to swap this over to radians, and also need to go to the wrench and make sure I'm in radians there. Okay, now that I'm in radians, the polar point was 3, pi over 4, pi divided by 4. Okay, I'm in caps. Let me change this so the pi symbol actually comes up. Pi, there we go. And so what does that tell me about the x and y values? That they'd be 2.12, which if you type that in the calculator would be 3 times the square root of 2 over 2. I would be willing to bet 3 times the square root of 2, all divided by 2. That is in fact 2.12, and all that changed. So we got number 1 correct. Let's try number 2. It says find the rectangular coordinates for the point 10, 52 degrees. Alright, well this time I need to have circles out to 10, which I only have 1, 2, 3, 4 lines. So I'm going to count by 3s. So this is 3, 6, 9, that would be, whoops, not 10, that would be 12. So 10 is going to be a little bit larger than 9 at 52 degrees. If I label the degrees here, I would have 15 degrees, 30 degrees, 45 degrees. This would be 75 degrees. 52 degrees. It's going to be in between 45 and 60 here. And the 10th circle would be just a little bit past 90. So it'll be somewhere kind of floating around right in here, this general area. That would be our point B. This says find the values in rectangular. So it's just the same formula we used last time. And you know what I should have done last time, I did not do it, is to show you what we're trying to do is find the values in terms of an x-axis and y-axis. In terms of x and y, where that point would be located. That's ultimately what we're trying to do here. Let me go back very quickly to the previous problem, and I'm going to show you this. Over here, the values that we came up with at 2.12 and 2.12 for x and y, what that was referring to is my x and y axis here and here. that this would come down and it would be just past the value 2. If I measured that down, measure this across, you can see it's just past that circle there on both sides. So that's why that value, were these two values, 2.12 and 2.12. They're just past those second circles. That's what we're finding out there. Let me get this a little bit drawn accurately. Okay, so now I'm trying to do the same thing here. So if I were going to estimate, again, my picture is not accurate or exact here. I had to estimate just plotting it. It looks like it's going to be around 6, and over here 3, 6, maybe around 8, I'd guess. So we could take a guess that's going to be C, but if we want to know for sure, we'd follow our formulas that x equals r cosine theta, which means the x would equal 10 times cosine of 52 degrees. And I'll go to the calculator for this in a second. The y value would be r sine, which means our y value would be 10 times the sine of 52 degrees. Come over to our calculator. I'm going to refresh this. When I refreshed it, put me back in degree mode, which is what I need to be in. They gave me a polar point. So 10th circle at 52 degrees. It looks like the point is 6.16 and 7.88. Our guess was correct. So that would be our guess here. Say x is approximately 6.16 and y was approximately 7.88. All right, and number 3 in the bell ringer. It says find two pairs of polar coordinates for C, and this is a rectangular coordinate. That's an x and a y. Whereas the previous problems where we were dealing with polar, r and theta, on this particular problem we'll be dealing with x and y. And it says find those values between 0 and 2 pi. So if I wanted to graph this one, I would need an x and y axis. This says go 2 units left and 5 units up. 1, 2, 1, 2, 3, 4, and 5. It's my x-axis, y-axis. Here's my point C. We want to know if we were going to find this in terms of polar coordinates, what would that value be? So we need to find the radius here, if you will, or hypotenuse if you think of it like a triangle. If you think of this in terms like a triangle here, we need to find out what's the radius and then also what's the theta. So we're looking for r and theta here. That's what we're looking for. So how do we do that? Well, we know that the x value is -2. We know the y value is 5. So if we do Pythagorean theorem, our r value will be the square root of x squared plus y squared. That's always our formula. So in this problem, it's the square root of -2 squared plus 5 squared. -2 times -2 is 4. 5 times 5 is 25. So we're looking at the square root of 29, which I do not think can be reduced. It's going to be some value between 5 and 6. Some value between 5 and 6, which immediately throws out these options. The radius had to be longer than 5. So these are out. So we're dealing with 5.39 as our radius here. And now for the theta, since it's on the left side, since theta is less than 0, I'm sorry, since x is less than 0, since x is negative, for our theta, we're going to do the inverse tangent. And I'm looking at the answer choices, it appears they're in radians. So I'll do the inverse tangent of y over x, and then I'm going to have to add pi. So what's going to happen in the calculator is it's going to calculate y is 5, x is 2, -2, excuse me, and then we'll add 3.14 to the answer to see what we come up with. So I'll just use this calculator. It'll do all the calculations for me. I go rectangular this time. The value was -2, and the y value was 5. I need to be in radians. That's what it looks like the answers are to me, radians. And I'm going to move this over to radians. Okay, and so what does that tell me? My radius is 5.38, which is the square root. I'm hopeful is the square root of 29, square root of 29, 5.385, yep, that's it. And then the theta, it's going to do exactly what I told you, and it gets 1.95. 1.95 is what it solves here for theta. So 1.95, here it is, D. Now if you're wondering, where does this answer come from? Well, if you have a negative magnitude, that means it's looking at it. A negative magnitude is kind of like thinking where you first were looking this direction, but then you go across. Now how do you get a negative magnitude? Well, you add 3.14 to this answer. So if I take my theta here, my theta 1, and add 3.14 plus pi, I get 5.09, which is that answer, which is just saying, okay, what if we wanted the negative magnitude? That means that we'd have to add another angle all the way around. So instead of stopping right here at point C, I would go around this way one more time. So I would need to take my theta and add pi to get there. And that would take me all the way around. Thus we would get that second answer. 11.1. What are we going to do here is we're going to start looking at some statistics. I'd recommend opening up your pre-programmed graphics calculators. I already have mine open on the left side of my screen here. I'd highly recommend for you to do the same because we'll be using that throughout. So we have a bunch of new vocabulary as we get going through. I will explain as we go. So first thing we're going to talk about is how a distribution, when we look at statistics, we'll talk a lot about distributions, which is just saying we have a bunch of different values that are related together in some way or some fashion. If we wanted to talk about those, we could say they're symmetrical, that is, if the values are evenly dispersed, or they could be skewed. In this particular one, we'd say it's skewed left when we have a tail of values going way out to the left, but not to the right. So this one was evenly distributed, not this one. This one has a lot more going left, or a tail looking thing going left, so we'd say it's skewed, or it's negative or left skewed distribution. A positive or right skewed distribution would be if the tail went right. So that's an idea of, and you can get through here some more of the nitty gritty of the definition, but that's an idea of skewed distributions or symmetrical distributions. So when we look at these, there's going to be different type of summary statistics we might choose, and it's all going to depend on the distribution. So these are just some general overview, but I'm going to walk you through how we would find these using our calculators. So on example 1, we want to look at this. It says a person's golfing. 20 members of a golf team actually hit a golf ball as far as they could. So each one of the 20 hit a golf ball. The table shows the distance each team member drove his or her ball. Construct a histogram and use it to describe the shape of the distribution. So what I'm going to do here is I'm going to open up this AP Statistics calculator. And I'm going to make it a little larger here so I can see better. And what we're going to do is we're going to type in these 20 values into my data set. And I'm just going to leave it all as X. So I have 185. Another 185, then a 190, 190, 190. Got the first 5 in. Now 200, 200, 200, 200, 200. That second row is pretty easy. Now we have a 210, another 210, 210, 210, and a 210. Okay, so that one was easy as well. 5 all 210. Now we have a 215, 215, 215, 270. And 280. Two people really know how to drive that golf ball. So I have my values in here. There's the 20. Now we're going to create what's called a histogram. So once you have your data set in, if you want, you can minimize that, but I'm going to go to univariate. That just means there's one variable we're looking at. We don't have two things going on, only one. So when I open this up, I want to see the histogram. So I'm going to click that and then click this box. And what happens is our Desmos shows us kind of like the box graph of our data. So let me scroll over here. All right, so the first problem wants us to construct a histogram and then use it to describe the data. Well, what I'm going to do here is I'm going to just drag this picture over so we can see the data. What that's doing is it's listed how far people drove the ball. Now notice they never drove at 180. So the smallest we ever drove was 185, and that's why this doesn't start at 180, but at 185, and this is showing how many people actually drove that value, which I didn't quite catch enough of that when I screen captured. Let me try this one more time. I'm sorry about this. Let me capture that value. Okay. So our histogram will show us not only the values that they drove, but how many people. 2 people drove 185. This would be 190. 3 people drove that. 5 people drove 200. 5 people drove 210. We had 3, 215. 1 here at 270 and 1 at 280. And so that's how a histogram looks. Now this data appears to me to be skewed to the right because we have that tail coming off to the right. And so that's what we'd say, that it's been skewed right. So on, I didn't actually, okay, so let's say positive. Or skewed right. Now in part B it says, summarize the center and spread of the data using either the mean and standard deviation or the 5-number summary. Justify your choice. Okay, so it's saying pick between the two. And so when I scroll down over here, you have all these values that it's talking about. So first we have 20 total values. Here's the mean, that means the average. So grouped together, we will have mean, and you will see this symbol, it's mu, is actually what the symbol is, mu, but we call it mean. The mean is 209.25 yards. That's our mean. This standard deviation, we'll take this symbol here, and we will say the standard deviation, which we'll get into in the following days what that actually means, is 24.6 yards. Now the 5, so there's the mean and standard deviation, or the 5-number summary. Now what's the 5-number summary? It's these values. We would say the minimum here is, that was the smallest value, was 185 yards. The quartile, which some people just call Q1, the first quartile is comprised of 195 yards and less. The median, or the middle, which would be 205. And then we have a quartile 3, Q3, which is 212.5. And finally, the maximum listed at 280. Now, when we list these out, we're supposed to justify our choice of which set of statistics is more valuable. Well, if you go back to these rules over here, we would see that when choosing the measures of the center and spread to describe the distribution, first examine the shape of the distribution, which we did, is skewed right. If the distribution is reasonably symmetrical and free of outliers, use the mean and standard deviation, but it's skewed. So this time, we would use the 5-number summary. Because it's skewed, we would use this data, because this was skewed right. Since we were skewed, we would use this particular data. So now with that piece of information, let's allow you to try this problem. All right, let's take a look at example 2. Bimodal distribution. Bimodal distribution. So it says cell phones. People from 2 professions were asked how much they paid for their work cell phone. Construct a histogram and use it to describe the shape of the distribution. And just one more time from example 1, we talked about 3 different shapes that you might see when we have a negative or left skewed distribution, is when you have a tail going to the left. Symmetrical is when it looks kind of like a upside down parabola, if you will. They're just even. You could cut it and you'd have basically the same type of distribution on both sides, or relatively the same, kind of like it's mirrored through the center. And then, or a positive right skewed would be if the tail went to the right. So that's what they mean by look at, a histogram here to use it to determine the shape. That's what we're going to look at. So I'm going to come over to my data set here. I refresh my calculator, so start fresh again. And I'm going to type in the values. We have 50, 50, 55. We have 3 55s, it looks like in a row. Then 5 60s. And then a 65, 70, 90, 95, 95, and then a whole bunch of 100s. Looks like 6 of them. And then three 105s. Okay, so I've typed these all in, and I'm looking on here. There's 5, 10, 15, 20, 24 pieces of information. If you go down to univariate statistics, you'll have a pretty good idea if you typed in at least the complete list. By this N right there should be saying 24, and it does, so that's pretty good. I'm going to click this histogram button. Oops, I'm going to try click that again. I'm going to minimize the data set just for a moment. And after you click the histogram, you see this little plus right there, zoom fit button. If you click that, you will see the distribution. So I'll screen capture this so we can have an idea what the data looks like. The data looks like this, but this doesn't match any of our distributions we saw, or the when we were looking at how it could be the different, whether it be positively skewed, symmetrical, or negatively skewed, left skewed, right skewed. When we looked at those pictures, this doesn't seem to match any of those. It seems to me like there's two different sections of data. Here's one over here, here's one over on the right side. So this is what we call bimodal. It looks like two different symmetries, if you will. That's what we call bimodal. So we have a data set over here and a second data set. So I'm going to say like this first grouping, first group, and the second group is over here. So it looks like to me there's just two different groups. They don't connect together. It looks like they're two different, when it talks about cell phones, it looks like it's two totally different plans. They're not even related in that regard. So what we would do is, if you were going to try to solve for this, so here's the histogram, describe the shape, it is bimodal. That's the shape, bimodal. So what do you do when it's bimodal? Well, let's go to part B. Part B, again, here's our data. Part B says to summarize the center and spread of the data using either the mean and standard deviation. That's when it's perfectly symmetrical, or the 5-number summary. Now, it looks like to me, the one on the left, if you were going to try to connect these just to see what the shape would look like, let me connect it kind of like they do with the straight line. If I can draw this, I'm going to kind of come up here. Well, you know what? I can't accurately enough on my little pad seem to hit this value. But if you look at it, it seems to me like this value would have a tail going to the right. So I would say this is skewed to the right, or positively skewed, this data over here. And if I did the same over here, it looks like this one's skewed left. Either way, they look skewed to me. So I'm going to use the 5-number summary, because that's what you use when it's skewed. So both bimodal groups of data seem skewed. Since they both seem skewed to me, I will use the 5-number summary as opposed to the mean and standard deviation. But here's the deal. If you're going to do that, you need to do it for each set of data. So I'm going to, again, list this off. It's kind of like calling this the first group or the first data set. And then we'll come back and do this second data set over here. So how am I going to do that? Well, what I'm going to do is I'm going to come back to here, and I'm seeing that there's this break at 80, like somewhere around 80. So any of the values that were greater than 80, I'm going to remove from here. And so I'm just pressing the delete button is all I'm pressing. And so now I've deleted those values. I'm going to come back over here, and I'm going to look at my histogram. And for this first data set, if you wanted the mean, which again we use that symbol mu to represent the mean, it'll be 58.3. The standard deviation, which it takes the symbol sigma there, is 5.8. And I'm rounding, so honestly I shouldn't be doing these equal signs. I should be doing squiggly approximate signs. But those aren't that's the mean and standard deviation. We're not taking those. We're going to use the 5-number summary, which starts with the minimum, and then it has this interquartile, the median, and the max. Okay, so the values, I'm going to list them in red here. For the first, the minimum for this data was 50. That was the smallest number we had. We had 50 listed twice using this histogram. It's 50 occurred 2 times. Quartile 1, that means the first 25% of values are 55 or less. So 25% of these values over here, which I think there's 12 of them. That means 4 of the values, so you can see 1, 2, and if you took 2 from here, 4 of the values are 55 or less. That's the first quartile. The median is literally like the middle value. On this one, since there's 12, it would be the value between 6 and 7 if you average them out, which this is just saying the median is 60, so they're probably both the 6th and 7th value are probably 60. Let's see it. 1, 2, 3, 4, 5, 6, 7. Yep, the average of these two. Now, why I said that is with 12, you have 6 in the first half, 6 up here in the first half, 6 in the bottom half. So the median would be the average of those two. That's where the calculator is getting its math, which average of 60 and 60 is 60. Quartile 3, that means the 75% of the values, 75% of the values are 60 or less. So again, that means if there's 12 values, 75%, 3 goes into that. I think I said 4 earlier. I was wrong. A quarter of 12 is 3. So the reason this Q1 is that 3 values are 55 or less. Quartile 3 means 9 values are 60 or less. 9 values. So 1, 2, there's 3 more, that's 5, that's 10, that's right. 9 values are 60 or less, and the maximum is 70. It means the highest value on here, that's 60, 65, 70. The highest value is 70. This would be the 5 summary. Oftentimes we'll talk about the interquartile. The interquartile is what 50% of the values are in between Q1 and 60. So if you see like interquartile range, anything like that, that's talking about the interquartile range, which would be Q1 is less than or equal to X, which is less than or equal to Q2, is from 55 to 60. So oftentimes you'll see that. So I just want to make sure you're aware what that is. Okay, so now let's take a look at the second data set. Okay, so in the second data set, I need to come back here and plug in these values. I actually need to change my picture back. Okay, so we're looking at starting with the 13th value. So there's 5, 10, this is 12. We're starting with value 90. So I'll have 90, 95, 95, 100, 100, 100, 100, 100, 100, 105, 105, and 105. Okay, so now I have these 3 values. Okay, let's scroll down and see what we can learn about this one. Well, if we wanted to know the mean in the second group is 99.6 approximately. Let's go approximately 99.6. The standard deviation is approximately 4.5. Now for the interquartile range, the minimum is 90. I am sorry, the 5 summary, the minimum is 90. The interquartile means from Q1 to Q3. Okay, so Q1 is 97.5. The median is 100. Quartile 3 is 102.5. And the max is 105. Okay, so when we look at this second data set, so 3 values were 105. So this is talking about the first 75% would occur right on that line between 100 and 105, and so that's why they take the 102.5 here. The maximum is at 105, the minimum was at 90, that's 80, 85, 90 right there. And interquartile 1, that means the first 3 values, you see it here, it's 95 or less, but between quartile 1 is between the value 3 and 4, and so they would average between this one and this, between 95 and 100, and that's where they get the 97.5. Again, I would use this one because it seems like to me this is skewed left or negatively skewed, so I would use this one. And the interquartile range on this one, interquartile range is from 97.5 to 102.5. Means over half the values occur between those two values in there. Or half of them rather. So that's the interquartile range. Half the values fall between those 2 points. Now here's one for you to try. So bimodal just means that there's two different data sets, or 2 different humps, if you will, to the data. So now you can use this problem to summarize and determine if it's negatively skewed, left skewed, if it's symmetrical, if it's positively or right skewed, or if it's bimodal. If you want to pause the video, get the data in, I will now go to the answer choices so you have those available to you. Just pause it if you need to. And here are your answer choices. Example 3. Now let's talk about what we call box plots. So we're looking at a box plot. We can talk negatively skewed, symmetrical, and positively skewed a lot easier than we could with the histogram, at least in my opinion, a lot easier. So this box plot is going to show us a picture kind of like this to represent the data. And so what's going to happen if something is negatively skewed? That means you're going to have this left whisker, that's what they call this left whisker longer than the right, and also the median, that's what this line is, will be further to the right than to the left. That's if it has a tail going to the left. Conversely, if the tail went to the right, you'd see it this way, where the whisker on the right is longer. This would be positively skewed. The median would be to the left, but there's a lot more values that extend out further this way than they would over here. And now symmetrical would be if everything looked pretty well the same. So on our data, for real quick, I'll give you a new example, but I'll just show you on this one. If I had switched from a histogram, let me take off histogram and open up box plot, you can see that this one was left skewed. See how that whisker is longer to the left than it was to the right? That would be left skewed or negatively skewed. Now let me put them one on top of the other, and you can see how this data, I think it's kind of, you can see that it does seem to be left skewed, but it's easier to tell on the box plot that it's left skewed, that the whisker is longer on the left side than the right. Okay, so now let's go to a new example. It says home sales. The table shows the prices of homes recently sold by a realtor. Construct a box plot and use it to describe the shape of the distribution. So let's go up to our data set, and this time we have new values. So we have 95, 110, 115, 150, 152, 154, 156, 165, 165, 168, 168, 170, 175, 177, 184. Okay, if I got this data in correctly, when I come down here, I'm going to hit the little zoom fit. And let me try that again. Zoom fit. There we go. And we see this data. Now, right now, there's not a whisker going out. This whisker is in here. That's because these values are what we call outliers here. They're outliers. But you can still see this is negatively skewed. Why? Because the median is not in the middle of this would be the interquartile range here. The median is shifted to the right. So this is still left skewed. Let me take a picture of this here. Give me a moment. Okay, now there's the data. So this would still be left skewed or negatively. Let me just say negative or left skewed. In which you could say skewed left if you wanted to as well. A little dyslexic there. There we go. This is negative or left skewed. Here's the median. Median is to the right. So since the median is right of the half, that means it extends out later to the left, so that all this would kind of represent the tail, if you will. The tail, how we kind of thought of it before, that side over here. So you see how this would have a longer tail. These are actually called outliers. Each one of these three things would be outliers, and this is called a whisker. Just so you have an idea what everything refers to, this would be the interquartile range in here. Interquartile range. And you can get the values. This would be from like 150 to 170, the interquartile range, and the median would be right there at 165. Okay, so part B. Now that we have that table, and I'm actually going to copy this one more time so we can look at part B. It says the table shows these same instructions. Table shows the prices of homes recently sold by realtors. Summarize the center and spread of the data using either the mean and standard deviation or the 5-number summary. Justify your choice. Well, I'm going to go ahead and list off all of the values again. So the mean, let me scroll down so we can see them all, is 153.6. I'm not rounding, so I just use the equal sign. The standard deviation, sigma, is approximately 26.3. Now, I would not use this value, though, these two values, because it's not symmetrical. So what I would use, though, is the 5-number summary, that the minimum is 95. Quartile 1, the first 25% of values fall 150 or less. The median value is 165. Quartile 3 is the height of the top, or the lowest 75% fall within 170 or lower, and the maximum is 184. Now this is what I would use. So the range of values are from 95 to 184, and the interquartile is 150 to 170. So I want you to see here, this is the mean, not the median, not the mean, but the median, and that's at 165. This is quartile 1, and you can see if you pull that down, that value would be 150. This is quartile 3, and you can see that that value is 170. The minimum value is 95. You can see that right there is 95. And this is the maximum value here, which it looks like it's 185 to me. 185. So that's how you can get all these values there. 185. You can see where those are found. Oh, it's actually 184, not 185. Looks like that must be just inside that line there. Yeah, it's hard to see. Let me show you on this one. If I zoom this in, it's not quite at, let me get 185 listed. There's 185. You can see it's not quite to 185. All right. Now I have one for you to try. I'll let you read this. Pause the video if you need to enter in your data. And now here are your whisker plots to look at. Your box plots, rather. Pause the video if you need to. All right, let's take a look at example 4 now. It says games. Jessica and Miguel earn these scores on a new computer game. Construct side-by-side box plots of the data sets. Then use this display to compare the distributions. So here's what I'm going to do. I'm going to use this calculator, and I've refreshed it, mine, by the way. If you just hit the refresh, it'll clear everything out. What I'm going to do is I'm going to enter these into the calculator, but what we're going to do is look at these as two separate data sets. So this one I will enter in as x1, and I will put y1 in as Miguel's score. So x1 is Jessica's scores, y1 will be Miguel's scores. So I'll come over here to my data set, and these will be two separate data sets. So I have 30, 30, 2 30s, 32, 34, 35, 35, 35, 36, 38, 38, 40, and 45. Now on the y1, I'll have 40, 60, 80, 82, 82, 84, 84, 85, 85, 87, 88, and 89. Now don't worry about what's going on down here. That is something we're going to learn about later. It's going to be comparing these two values. I'm not concerned with that. What I will do though is I'm going to hit the zoom fit here so you can see where the scatter points are. And what it's doing is it's relating the x and the y, which doesn't do much good because they're not supposed to be related to one another. But now I'm going to pull up the univariate statistics because honestly, that's what I'm doing. I'm treating these two variables as two separate data sets. I'm not working them together. I want to look at them separate. So I'm going to turn on the box plot here, and it's going to graph it really low. To make it easier to see, I'm going to change this offset here, and I'm going to make it go higher. I'm going to press the 20, and I'll make it go up a little bit higher to see, and I'll give it some more height just so you can kind of see the values. And I want to do a box plot also for the y1 data set. And so this one I will offset. We'll make it go up a little bit higher. Let's put it like at 30. And again, I'll give it a height of 3. And right now, we're not seeing many values. Oh, there we go. Let me kind of zoom out. You know what I'm going to do? I'm going to change this to 10 and 20. And let me kind of reset here so we can see where this data is. So you can see these data in here. Now, my values, I have a lot more x's that I need to look at. So I'm going to change my x-axis here. Let's make this only go left to 25 and make it go right to, say, 100. That'll kind of help us out so we can see this data better. And I could shrink all this down if I wanted to and not have it offset so high. So that's, I'm just kind of showing you how all this works. If I wanted to like lower both of these, let's just say I want that to be at 5. I could look at it this way. Let me see if I hit this zoom right there. Okay, so here you can see now all this data. I'm going to take off this scatter plot because honestly, I don't want them related together. Here are my two box plots, as you can see. And so that's really the values I'm looking at in there. Ignore what's going on there. Again, that's going to be later on. So this is the value that I really need. And I'm going to change one more thing. Here we go, the y-axis. There's so much extra here. How about we let's look from -20 to +40. And now we can see these. And again, I don't even need to go that high. I could lower it to like 15. 15, and let's just go to -5 here. And I'll put the heights at 1. So I'm just kind of walking you through how these relate to one another. Let's take a screen capture of what we have. And so you can compare the data. Now let me insert this in here. Oh, wow, that's really large. And so I kind of just not only showed you how to do the box plot, I showed you how to manipulate the data in the viewing window. So you can see how everything looks. Now there is one more thing I could do to change this. If you notice it's highlighted to exclude outliers. If I uncheck that, you'll see how it'll change the box whiskers. The whiskers now will go all the way through the outliers. Now typically we might exclude those, and so you would see a graph more like that. But if you wanted to see it without the or with the outliers listed in the whiskers, you would see that the graph would change like that. Let me do it on both of these. So what does that actually mean? That means one of the y values was way lower than the rest of them. Actually, both of these two are way lower than the rest. And that's why whenever I exclude outliers, you see these two values at 60 and 40 here off on their own. They're outside. We're going to learn a term for standard deviations in there in the following days, but that's where those come from. So I wanted you to see that. And now, so if we were going to compare the distributions or talk about them, we could say, well, the range of this box plot obviously goes from 30 to 45. The interquartile range would be these values. If we want it, we could run the statistic summary down here and look at it. And you could see that the interquartile will go from 33 to 38. That's those two values. If I wanted to see the interquartile of these two, I would just need to change this to a y1, y1, and a y1 there. And you would see those go from 81 to 86. So all together, when you start putting this stuff together, that's how you can compare and make generalizations about your data. If you need more than one data set, you just add a row and give it a new variable, which I just called mine y1. All right, with that, I'm going to let you try DOL number 4 here. Pause your video to get your data in. Do not worry about the dollar signs, just enter the numbers. And now I'll let you look at the different answer choices. Now example 5, football. The table gives the frequency distribution of weights of football players from 11 teams. Construct a percentile graph of the data. And so let me walk you through what this means. For given these different weight ranges, they're just showing you how many football players fall into these weights. So whenever you're coming up with a percentile graph, what you need to come up with is first the cumulative frequency, which means the total of that value and any previous. So on the first one, it's easy. The cumulative, that just means add up all the values, this one and previous, which would equal 46. For the second one, what we would do is we take the 46 and add 120. And so we would have 166. The next one, we would take this 166 and you would add 135 to it. And so on and so forth down this chart. And so this one will equal 200, this will be 301, I believe. If I'm doing my math right, I think that's 301. And so then you take your 301 and you're going to add 130 to this, which will be 431. Whoops. 431. And then I take 431 and I'm going to add 70, which is going to give me 501. 501. And then I'm going to take 501 and add 40, which will give me 541. 541 plus 34 equals 575. And finally, 575 plus 13 gives me the total, which is 588. So when it comes to cumulative percentages, what you're going to do is you take your cumulative frequency, which is 46 for this cell, and divide it by the total, which is 588. And this will be our cumulative percentage. So I'm going to come over here and just get a new line. 46 divided by 588. It's going to be basically 7.8%. 7.8%. Because that's not a percentage there. I moved the decimal over 2 times. And I should do approximately instead of equals. Let me do approximately, showing that we are rounding. And so the next one, we take 166 and divide that by 588. And I'm going to write all these out here. 301 divided by 588. Then 431 divided by 588. And then we'll have 501 divided by 588. 541 divided by 588. 575 divided by 588. And then finally, the 588, this one I don't need to do a squiggly equal sign, divided by 588. This one will equal exactly 100%, because that is the whole. So let's find out what the other values are. So we'll have 166, which is 28.2%. 28.2%. 301. It's 51.2% when I round, 51.2. 431 will be 73.3%. 501 divided by 588 is 85.2%. 541 is 92%. And finally, 575 would be roughly 97.8%. Okay, so first, once you construct all that, now we can get to the graph. Now for the graph here, what I'm going to do is I'm going to start introducing you how we can have two variables work together. What I'm going to do is to type this in as the x1 column. This will be kind of like my x1 column here. And this will be my y1 column. And I'm just not going to use a percentage. I'll just type in the numbers apart from that. And I'm going to add one value. This is saying that the lightest people are is 121. So I will add the value 120, or I should say 120. Anything less than or equal to that, less than or equal to 120, will occur 0 times, which means it would be 0 over 588, or 0%. Okay, so I just kind of added that in right here for my table. So the first thing I'll say is starting at weight 120 and less than that, it occurs 0 times. From here, what I'm going to do is put in the right value going across that way. So that's what I'm going to enter in here. So the next value I have is a range from anywhere from 121 to 140. And this happens 7.8 times. Then I will have the value 160. And this happens 28.2% of the time. 180 will go up to 51.2. 200 gets to the percentage of 73.3. 220 and less than that is 85.2% of the athletes. Weights of 240 or less make up 92% of the athletes. 260 is 97.8%, and 280 and less. 280 and less is 100% of the athletes. So here's my data here. As you can see, it's kind of modeled by this little squiggly curve. And so if you were going to predict something in here, we'd have to learn how to make an equation, which we haven't taught you yet. And so let me, now that I've graphed this, let me show you part B, where it says, and I'm going to screenshot these values. Actually, let me zoom in just a little bit. Okay. The screen capture now. Sorry. We can now make predictions on what we think the weight might be. A weight or a frequency amount. Okay, so now it says estimate the percentile rank of a player weighing 210. So this is counting on the x-axis by tens. I can tell it goes from 200, 210, 220, 230, 240, 250. So basically what we're trying to find out is if we had the value, a weight of 210, what would that approximately be for athletes? Like what percentage of athletes would that be? And so what I'm going to do is just kind of look at this. We will learn in the days coming that we can make what's called regression lines, which is basically we'll have values that kind of come through here that just predict where it would be, where each value would be on a consistent basis. And so I just added a line there, and now what I would do is I'd come in here and connect from 210 to my black line there, and then try to go across. I will say it's approximately 80% of athletes. So it says estimate the percentile rank of a player weighing 210 pounds would have in this distribution and interpret its meaning. I would say approximately 80% of athletes or football players. Whoops, football, there we go. Players weigh 210 pounds. I'll just do LBS or less. That's what the cumulative percentage does, is it just kind of makes a little graph, and it's weighing out the cumulative. That means you add up all the values that's at that point and previous. And so all the values over here, the total percent that's 210 pounds or less would be around 80%. So I'm not sure if it's exactly 80. This looks like it might be slightly under 80. This is 70 here. Maybe it's something a little under 80. But either way, you can kind of see the point of how you predict from here. So now that I've walked you through how to do one problem, you try this problem. Go through the same steps here. You've gotten this table, come up with your cumulative frequencies, and then the frequency percentage. So you'll want to come up with both of those values across here, your frequency and your frequency percentage, to come up with your graph that you're able to graph in this data set to make your predictions.